The proportionality theorem, the proof, requires some ingenious connections between area and length. Those are the only two ways we have to generate real numbers that correspond to segments or to correspond to anything geometric, right? And so I'm looking for a real number. I'm looking for four real numbers that create this proportion. And so I'm going to definitely need some ingenuity. Right, so the setup is that we have some arbitrary triangle and you pick any point, let's say on the segment AB, you draw a line that's parallel to the opposite side, so it's parallel to BC. And if you do that, then there's a proportionality between the segment, well, let me use the one that's drawn. So between segment AD divided by DB and segment AE divided by EC. So we get this proportionality happening whenever we draw a parallel line, right? So this can be any parallel line in here. Okay. So first, notice, and let me move this up so we can see a little better. Notice that the red triangle and the orange triangle have equal areas. So that's my first claim. And to see this, we're going to use a theorem that we proved in the last section, which is that parallel lines are everywhere equidistant. Okay. Well, first, we're going to construct the unique perpendicular. So let's do this. Let's look at this, right? We're going to construct the unique perpendicular through E that's perpendicular to BC. And we're going to construct the unique perpendicular through D that's perpendicular to BC. Okay, so the blue lines there are our unique perpendiculars, and we're going to claim that they have that they're congruent, that they have the same length. Why? Well, because again, we just proved in the previous section that parallel lines are everywhere equidistant. All right, so we define the distance between a point and a line segment as this unique perpendicular, the length of this unique perpendicular. Okay, so rather amazingly, the orange triangle and the red triangle have the same area. They're not congruent. We're not saying that they're congruent. We're saying that their areas, right? That their areas are equal. Okay, not congruent, but their areas are equal. Now, so oh, and this is just, now that they're congruent, they're also the altitudes of these triangles. Okay, this is why the areas are congruent. Sorry, right? So if I look at this triangle, this orange triangle, one way to calculate its height is to take the altitude times this base here, right? And the same will work for the other triangle. So you can see that they have this line segment in common, DE, right? Our parallel line segment. This one has DP, this one has EQ. Doesn't really matter, they're the same length, so we could do some substitutions later. But these are calculating the actual areas of these two triangles to see why they're in fact have the same area. Okay, so now what? Well, now we want to look at two other triangles that have the same area. And I've drawn one purple on the left and one blue on the right. It's a little difficult to see, but the purple triangle has the same area. All right, so let me just outline this, right? So the purple triangle that we're talking about is the triangle ABE. Okay, and the blue triangle is ADC. All right. Now, why are they congruent? Well, they're congruent because of axiom SG axiom 19, which says that the total area of the purple triangle is equal to the sum of the area of triangle ADE and the sum of the area of triangle BDE. In other words, when I have two polygons that are joined on these vertices and lines, DE, then to get the total area, I can add the sum of the two areas. Well, and I know that this triangle, DEB, I know that it has the same area as this one over here. And then they both share this area here in the middle. So we're just extending the idea that these two areas were equal. Well, I have this big triangle, so now we know that these two areas, the area of triangle ADC and the area of triangle ACB, are also equal. Okay, so what does that mean? Well, now think about it this way. Now we're going to look at the two triangles on the left and the two triangles on the right. And what do I mean by that? I'm talking about this triangle here, right? And this triangle here. And I'm going to compute their areas, but in a slightly different way. So remembering that I'm talking about those two triangles on the left, construct an altitude. Now, what's an altitude? An altitude is I go from E and I drop a perpendicular. Why? Well, because this altitude will be the height of both of these triangles, triangle BDE and triangle ADE, right? It's looked at from a slightly different perspective, right? But it is the height of triangle BDE, and same thing, it will be the triangle of ADE as well. Okay, so we're going to do that here. And so we're going to call this altitude EY. And note that it is an altitude of both of the triangles I just showed you. And we're going to do the same thing from D. We're going to drop that perpendicular, that unique perpendicular, over to the point X. And now it's a height, it's an altitude of both of those triangles on the right. It's an altitude of AED, right? And it's an altitude of CED. All right, so the figure's getting a little busy, but these are all true. Okay, now what? Well, now I'm going to take these areas, right, which are the same, right? Wait, I'm sorry. These areas are the same. Let me redo that. Right, these two areas are the same. It's the same triangle. I've just labeled it in slightly different ways. So we know that their areas are equal. Actually, those triangles are congruent. They're the same triangle. So congruent, equal areas, whatever you want to say about them. And then we can divide through by this value, the area of this, either of these two triangles. Why? Because their areas are equal, right? We found this to be true. And because that's true, I can divide through by that real number. Let's say there's some real number R. And so I can take the area of ADE equals the area of ADE and then divide through by the area of either one of these. You know, it's just some real number. It's the same real number. All right, that's what we're doing. And sorry, let me click. Right, so we start with the area of ADE, and we note that it's 1/2 the base times the height. The base is AD, and its height is the altitude, EY. Right, so 1/2 the base times the height. And then we're going to do the same thing, writing it slightly differently. We can look at the altitude dy. So I have 1/2 the base AE times the height, which is dx. Okay, but these are equal because it's the same triangle. Okay, and then, like I said, we're going to divide through by this value. And we can divide through by the one in orange on the left side of this equation and the one in red on the right side of this equation. But we're going to write those slightly differently, right? Let me make this point that we're using these altitudes now, right? We created the altitudes dx and ey. So even though we are in fact dividing through by these values up here, the area formula that we're going to use is slightly different, right? But let's check this out. Do I have it? So the base times the height here, right? So the base is dB, and the height is still this altitude up here. Yeah, so we have it. That's good. And then let's check out this other one. Sorry. So now the base EC, right, and the height of that triangle is dx. Yeah. So 1/2 the base times the height. Again, we've used this equality, but we've rewritten the area formulas to include that altitude. Why? Well, because of course the altitudes are going to cancel. The fractions will cancel. And so we have the proportion that we need. Okay, so again, this is a rather tricky proof if you've never seen it before on how to set it up, but I do want to make the point that we only have two ways to generate real numbers at the moment. We can only get real numbers in terms of area, and we can only get real numbers in terms of the length of these distances, right? The distances between 2 points. So to get a proportion like this, we actually needed to calculate areas that we knew were equal. That was the key, to have areas that are equal. Then we could write them in some different ways to get the proportion that we need, and also understanding the idea of an altitude being the height of a triangle, how to construct these different altitudes that we need to show that the triangle areas are the same.